In this video, we're going to learn about some of the basic ideas of graphing and equations and how they relate to each other. Just I want to first mention here that this type of graphing we're doing here, where we have our x and our y axes, there is a name for it. It's called either the rectangular coordinate system, because it's, everything's written out in terms of a rectangle. It's also known as the Cartesian coordinate system, named after a famous mathematician and philosopher, René Descartes. Feel free to read up and learn about him. Anyways, so when I give you an equation and I ask you to draw a graph of it, there are many different ways you go about doing this. You're going to learn different shortcuts for if it's a line, then we can do it this way. If it's a parabola, we can do it that way. If it's a trig function, we do this. And all these different processes here. The thing is that each type of equation is going to have its own little shortcut to draw a graph. And it's definitely good to learn all of these. But there is no nice shortcut that works for every single equation. In fact, the only good way that would work for just any equation you come across, and the one we're going to use right now, is the idea of making a table. So we're going to make ourselves a nice XY table, and we're going to use that to draw our graph. Now, the way an XY table works is you pick whatever values you want for either X or Y. You plug them into the equation, then you solve it for the other variable, and you use that to then draw a point. Now this is a kind of long and tedious process here, especially because unless you know what shape it is, you don't really know how many points it's going to take before you can figure it out. For example, if you have a line, all you need are 2 points. You connect them and there you go. If you have parabola, you're probably going to want 3 points to do it. And then different other shapes, you might want 4 or 5 points. But the thing is, if you don't know what shape it is, who knows? So we're going to do kind of maybe overkill right now. We're going to do a lot of points, because the more points you can do, the more accurate your graph will be, and that's certainly going to be helpful. Again, it is a tedious method here. It's not one you'd really like to do too often if you can avoid it. But it is in fact a perfect method for a graphing calculator or a computer, because long, tedious calculations are exactly what those were created to do. So what I'm going to do is I'm going to go ahead and go some, I don't know, how about -2, -1, 0, 1, 2, and I'm going to plug each of those in for X and see what my Y is going to be. And as I said, I don't know if those are going to be the perfect correct numbers to try. Maybe I should have done 0 to 5. Maybe I should have done -5 to +5. Maybe I should have done 100 to 110. I mean, again, you don't really know unless you get more experience at this what good numbers might be to try. But you just got to try and see what happens. Now, if I go ahead and plug in -2, maybe I'll show my work over here on the side. Y is -2 cubed minus a -2. That's going to be -8 plus 2, and we're going to get -6. So that means my first Y value here is a -6. Okay, so now I'm going to go ahead and plug in -1. This time I won't show the work, but you can check it. -1 cubed is -1. Minus a -1 is +1 is going to be 0 there. Plugging in 0 gives 0 pretty easily. Plugging in 1 is also going to give 0. And then if I plug in 2 there, I would end up getting +6. So right now, what I would have is I would have the point -2, -6, -1, 0, 0, 0, 1, 0, and +2, +6. Now, I chose those numbers because they're nice whole numbers. You plug them in, not too much trouble. But if you look at our graph now, if you try to connect the dots, it's not going to actually give you a very accurate graph. So at this point in time, you'd really want to plug in other ones, maybe not always whole numbers. Maybe plug in 0.5 or negative 0.5 or things like this. I'm going to save us a little bit of time here and just kind of show you what the graph's going to be, but I just wanted to point out this example here that if you only pick nice whole numbers, you won't always get a great shape for what the graph is. However, in this graph, it's going to look something like so. And we are going to see in a later section exactly how you could get this graph without plugging in a ton of points. There is a process to it for x-cubed graphs. Okay, so great. So we got that part there, not too much trouble. Next thing we want to do is we want to say, okay, if we have a graph, what are some special points? In fact, we have multiple special points here. And we're going to give them different names. The first name is going to be an X-Intercept. An X-Intercept is a point on the graph where it crosses x-axis. And similarly, a y-intercept is a point where the graph crosses the y-axis. And so turns out that every x-intercept, every one of these x-intercepts has a y value of 0, and every y-intercept has an x value of 0. And so if I give you a random equation here and I ask you to find the x and y-intercepts, well, that's how we're going to do it. So to find the x-intercept, we're going to go ahead and plug y equal to 0 in. Now if I do that, I'd have 0 minus 0. 0 is x squared minus 5x plus 6. We go ahead and factor this. We're going to get two different values for x. Now, those x values by themselves, those are not the answer. The answer is the point, 2, 0, and 3, 0. These are our x-intercepts. Then, if I want to find my y-intercepts, I'm going to plug in x equal to 0. So then I would have y squared minus 5y is 0 minus 0 plus 6. That'll give me y squared minus 5y minus 6. Then this is going to factor differently than before. It's not 2 and 3. It's going to be minus 6 plus 1. So we're going to get the values y is 6 and y is negative 1. But again, those are not the actual points that we're looking for. The points would be 0, 6, and 0, negative 1. And this is how we find our x and y intercepts. We plug in 0 for one variable, solve for the other variable, and then repeat the process. Okay. Now, once we passed our intercepts, the important points on our graph, we now are going to look at something about the shape of the graph called symmetry. Now, you've probably encountered symmetry in your life. So the idea is that when a shape is, symmetric, it looks the same on either side. It doesn't look off or unusual. It's all in a nice fashion there. For example, circles are about as symmetric as you could possibly get. And so what do we do with these things? We'd like to know whether our equation is going to look like that or not. And there are lots of different varieties of symmetry out there, but at this point in time, we're only going to study 3 of them: x-axis, y-axis, and origin symmetry. So the idea of an x-axis symmetry is that whatever shape that you have on top of the x-axis, you are going to have the same shape on the bottom of the x-axis. In other words, if you could imagine folding your piece of paper along the x-axis, the two sides should line up perfectly. Now, if you look at my actual picture here, that's not the case. It's because I'm not drawing things perfectly at all. But if you want symmetry, it has to look like that. Y-axis symmetry is the same thing, but now instead of going around the x-axis, it's now going to be around the y-axis. So again, if you were to put a little dashed line on the y-axis and fold the paper there, the two sides would line up nicely. Okay, so that's x-axis and y-axis here. The origin symmetry is not as easy to see visually, but what it works is that whatever you have that's going up and to the right from the origin, you also have to have the mirror image that is down and left and so on. So that would be something that's like an origin symmetry. And if you had something coming down like this, you would need to have the corresponding shape in the right bottom corner there. So again, the idea is it goes around. Now there's a quick way to test these here. If I want to test the x-axis symmetry, what I do is I replace y with negative y, and if I still have the same equation, that means it is symmetric, and if I get a different equation, that means it is not symmetric. Similarly, for y-axis symmetry, I'm going to replace x with negative x and see what happens to the equation. And lastly, symmetry about the origin, I'm going to replace both the x and the y and see what happens there. So we're going to go ahead and take a look at the equation y equals x cubed minus x, and we're going to try to figure out any symmetry that this equation has. Well, if I looked at my picture there, I could see it definitely doesn't have x or y-axis symmetry because it's not the same top, bottom, or left and right. However, we can just check that really quickly here. For x-axis symmetry, I replace my y with negative y. And then if I were to solve for y here, I'd get negative x cubed plus x. And that is not the same, that is different than the original one. And so that means there is no x-axis symmetry. For the next one, if I want to check the y-axis symmetry, I replace the x with negative x. And this time I would have negative x cubed plus x. Again, that is different. So that means there's no y-axis symmetry. And for the last one, I replace y with negative y and x with negative x. And then once I go ahead and divide by the negative there, I get y is x cubed minus x. And this right here, this is the same. And so that means that there is origin symmetry. So these are just a couple of quick little ideas about graphs and things that we're going to ask you to check on. Just a little different procedures here you should know.